7.8 kips. And we know the magnitude of EY is 220, oops, those aren't kips, those are newtons. 222.2 newtons. And that's all we know. Your best bet for answers is invariably a horizontal or a vertical member. You'll get answers quicker by pulling that piece out for first consideration than if you pick a slanted member. This slanted member would be a horrible choice. If you sum moments about A, you have 4 unknowns still having moment arms. No answers are going to come from that. No good's going to come from that thought. If you sum forces vertical, you have 2 unknowns. Not a good choice. Sum forces horizontal, 3 unknown horizontal forces. Not a good choice. Slanted members should be left till last. Pick a horizontal or a vertical member. If you sum moments about B, then BX will have no moment arm, BY will have no moment arm, DX will have no moment arm, and therefore only DY will hang out, and we can solve for the force in member DY. Sum moments about B equals 0 is equal to minus 500 newtons. He is 8 meters away from the moment point. I called that tendency to roll a negative number because worried to get away from me, he would roll about point B in this direction, and that is not right-hand rule, and therefore I called it a negative tendency to roll. Plus dy times his moment arm, 20 meters. That's all the forces acting. dy is equal to 200 newtons of force. I list that once, and I list it twice. It always hangs out 2 times. Here it is down here. 200 newtons. Now it's easy to sum moments about point D. This one is so simple, though, I think we could probably sum forces vertical without much worry. Sum forces in the vertical directions equals 0 is equal to plus BY minus 500 plus 200, and BY is 300 newtons. I list it once. I list it twice. If you forget to go list this the other time, then when you come to the next free body, you'll think there's more unknowns than there really are. Alright, now there's nothing else I can do with this free body, member BD. Anytime you run out of things to do, even if you're not sure you see what else to do, don't worry about it. Just skip over to a different free body and use it to pick up some answers. For example, member CDE. Member CDE has 3 unknowns acting and 2 things I've already found. To get rid of 2 of them, as many as possible, I'll sum moments about C. The reason being, 2 unknowns pass through point C, and they therefore drop out of the equations. The equation reads, sum moments about C equals 0 equals. First, there is a dx force. He is 10 meters away from point C. Now, he may look like he's further than that, But it's your job just to take a piece of string and tie it from the point C that you're summing moments to the closest distance that force ever gets. And that force gets within 10 meters of the pin. The tendency to roll for that force is this way. Were he to get away from me, I don't intend that to happen, but that would be a negative tendency to roll, not the way my right hand is made. Next, I see a dy force. Oops, I should have just written down 200 newtons. His moment arm is, well, let me follow dy. Here's where dy goes. This is how close he gets to point C. He gets within 10 meters of the pin. So his moment arm is 10 meters. His tendency to roll where he to get away from me is downwards and on around like that. He is also a negative tendency to roll. So I put a minus sign in front of his rotation tendency. Finally, I have 222.2 newtons. His moment arm, I follow his line of action till he gets as close to point C as he's ever going to get. That's 18 meters away. His tendency to roll is positive, and we solve for dx.
It's 200.
200 right on the money. Somebody worked this problem out so it would come out even. Did the answer come out a plus sign?
Yes.
Did, so that means that the arrowhead is properly shown. And once you get a couple of these things, then you just got them all on the run. Once you've got dx is 200, then it's a snap to solve for cx. You simply sum forces horizontal. And then you solve for cy. You simply sum forces vertical. And then you put cx and cy on the next free body over on member ABC, and you sum forces horizontal and vertical. The first sticking point is a couple of these sum of the moments equation, and then everything else just falls out. Alright, so that's frames. Alright, let me mention on page 18A, this is the member we just looked at, member CDE. And someone asked me to solve for the forces inside of the member, 4 meters above point D. So what I did is to expose the forces inside the member at that point. I cut the member and isolated the bottom half of it. I could just as easily have cut the top half out. In fact, probably would have been better because there would have been fewer forces acting on the structure. But either way works nicely. Here's how you'd solve for the forces inside the structure. You would simply break dx up into its components. It'll have a component transverse and parallel to the member. You know this angle right here. This angle is 8. Oh, it's a 45 degree angle. It's not drawn much like it, is it? It's an 8 by 8 angle, and therefore you simply put 45 degrees in here and 45 degrees in here and multiply the 200 Newton force times cosine of 45 degrees.
141.
141 newtons and 141 newtons. This guy here is a piece of the reason P cut is there, because he's pushing up and P cut is having to resist. The same way with the 200 Newton force. You will break it up into its components, parallel and transverse to the member. Then you'll take the EY force and break it up into its components, parallel and transverse to the member, and some forces along the member's axis to get P cut. P cut would equal to the 141 component, subtract DN's component, add EY's component, and that'll give you P cut.
Turns out it's 15.7.
Turns out 15.7. Okay. Take a chance on that. It certainly could be. You do the same thing for V, the shear across the axis of the member. You simply sum forces in the transverse direction. And then to get M cut, you simply multiply each of the forces times their moment arms. I don't care about V cut. Let me get M cut.
Well, this one right here is 157.
157.
Yeah.
Sorry
about that.
Okay. M cut would be caused by the 200 kilonewtons transverse force of 141 kips, 141 newtons. And this dy's moment and this EY's moment. You'd simply add up each of those forces' moments, multiply times those forces, multiply times their moment arm to solve for M cut. Well, let's see, if this one's 200, 141, these guys were both 141 also, won't they? And what is 222 broken up into two components?
Adam was 157.
157 and 157, okay. Here's what I'd write down for an equation. I'd say that the sum of the moments about the cut face is equal to 0 is equal to, first, there is a M cut. I write that M cut as minus because he doesn't roll like my hand is built, a right hand rule. Next, I put in the 141 Newton force times his moment arm. His moment arm is, I'll tell you what, rather than find that moment arm, why don't we just take the original 200 Newton force and multiply it times 4 meters. Give us the same thing. So that would be minus 200 newtons multiplied times his 4 meter moment arm. And here is our 200 Newton force for dy. So there's a 200 Newton force multiplied times his moment arm, 4 meters. His tendency to roll is also minus. And finally, we have a 222 Newton force, and his moment arm is 12 meters. His tendency to roll is positive. One equation, one unknown. Solve for M cut.
1,066.
1066, close enough.
Yeah.
Newton meters. That's the way you get the forces on any of these things inside any of these members. This also works on a beam. All right. Now then, one of the things that a lot of problems called for, whether it be under a footing of strange shape, or whether it be a weld, where you were asked to get the strength of a weld, or a group of bolts, was being able to find centroids of areas. Now here, for instance, looks like a flat plate. Perhaps it is the end view of a beam of various and sundry pieces, and they want to know how far to the right does the centroid lie and how far up does the centroid lie. The rule is draw a reference axis at the base. Secondly, break the shape up into pieces that you understand. For instance, I can divide this piece up into a triangle and a rectangle and then a triangle. That's what I've done in the first one, and I fully understand those little pieces. I understand how big they are. This is a rectangle, base height. This is a triangle, 1/2 base height. This is a rectangle, base height. This is a triangle, 1/2 base height. And I fully understand the locations of their centroids. Here's where I'd put the pin to make sure that little rectangle won't roll. If I were to spin it about that point, it would just arbitrarily come up wherever it wanted to. It wouldn't always tend to fall with the big end down. Here's the centroid of that rectangle, approximately. Here's the centroid of that triangle. Here's the centroid of that triangle. If you call this Area 1, Area 2, Area 3, and Area 4, then the distance from the reference axis, these are given the name Y1, Y2, Y3, and Y4. Your equation for how high is the centroid is given by Y bar is equal to A1 Y1 plus A2 Y2 plus A3 Y3 plus A4 Y4 plus A5, however many of these things you've got, you just add them all up and you divide by the sum of the areas. You just divide by the sum of the areas, and that'll tell you the location of the centroid of the entire piece. Now then, over on the right-hand side, you'll notice I divided it up instead into one big solid piece with no missing corners. That's what I'm going to call Area 1. That, of course, happens to be untrue, and therefore I admit that Area 2 is removed from Area 1, and Area 3 was removed from Area 1. But it works exactly the same. The only difference is, in this case, Area 2 and Area 3 will be subtracted from your equation because the pieces are missing, as opposed to being added. So this one would say Y bar is equal to Area 1 times y1 plus area 2 is a minus number times y2 plus area 3 is subtracted times y3 divided by area 1 plus a minus area 2 plus a minus area 3, because they're missing. The only reason I say that is a lot of times it's a lot quicker to get answers rather than having divided up into, like this case, there were 4 areas. Here, if you simply take off some pieces, you only have to mess around with 3 areas. X bar, the horizontal distance, will be exactly the same. The only thing you do is you lay your paper like that, and you go up and down again. All right. Page 19. They ask us to locate the centroid of the object shown. I think it would be the quickest to break it up into a piece and a missing piece. So I'm going to tell you area 1 is the piece including everything. Area 2 is the missing piece. Area 1 is equal to 8 feet by 8 feet, 64 square feet. Area 2 is 4 feet by 4 feet, but it's missing a minus 16 square feet. Now, there's not much need for me to solve for the up and down location of this centroid. Due to symmetry, it's right in the middle. The centroid is actually the location. If you would cut this out of a piece of cardboard and balance it on a knife edge, that's where the centroid is located. And I know due to symmetry I could balance that piece of cardboard on an XX axis right as it's shown. I'll tell the guy the answer is 4 feet and 4 feet for the up and down location. So I assume his real interest is how far is it to the right, X bar. The equation for X bar is area 1 times how far is area 1 centroid from the reference axis, and this is the reference axis. Well, it's an 8 by 8 chunk. An 8 by 8 chunk is halfway out down the 8-foot dimension. That's 4 feet out to the centroid of a rectangle. Plus area 2. Well, that's a 16-foot negative square feet. His centroid is right here, and that is 8 feet out and 2 feet back. So that's 8 feet minus 2 feet back for his distance. And then we divide that by the sum of the areas. 64 square feet plus a minus 16 square feet, and whatever that comes out, that's where the centroid is. Incidentally, that's where you would want to place the equivalent uniform force underneath the footing so that you'd get uniform pressure underneath that footing. If you'll cause the soil pressures to act through the centroid, then the stresses underneath that will be uniformly distributed. What'd you get for that?
Answer's 3.33.
3.33 feet, thank you. All right. Same way with page 20. Page 20, you could take it as a big solid piece and then subtract off some pieces. I think that'd be foolish. In this case, it's just too easy to cut it up into 3 little chunks. The centroids are here, here, and here. Those are your Y1, Y2, Y3. The areas are A1, A2, A3. Piece of cake. And obviously most of these equations are in the notes. Now then, the moment of inertia of something, the moment of inertia of these shapes will always be found about the centroid. So this I total, or just normally called I, is actually I about the centroid. That's because everything always tends to bend about the centroid. When you took ME 212 or whatever, they made you find a moment of inertia about the base, moment of inertia about 2 feet up. Well, those were good practice, but you don't make any money with those. The one that is worth something is the moment of inertia about the centroid of a shape. So once you find the centroid of the shape, you need to find the moment of inertia about that centroid. If you're working on a weld problem, you'll find the centroid of the welds, and then you'll find the moment of inertia about that centroid. If you're working with a group of bolts, then you'll find the moment of inertia about the centroid of those bolts. Now basically, I0, you look it up in a book. It's actually the integral of a y squared and all that stuff. But the moment of inertia of anything that you use is in the book. For instance, rectangles with base B and height h have an I0 term just because they're there. It's given by the base times the height cubed divided by 12. If it's a triangle, has a moment of inertia about its own centroid. If it's a circle, has a moment of inertia about its own centroid. If it's a half a circle, has a moment of inertia about its own centroid. Those numbers are in any strength of materials book. Now the transfer moment of inertia, anytime an area or the area's centroid is off of the neutral axis, or the centroid of the entire area that you just found. In other words, anytime one of the little area's centroid is off of the whole shape's centroid, or the neutral axis, then you pick up a transfer moment of inertia along with the I0 term. And that term's not in the book. Doesn't need to be. Transfer moment of inertia is always A times the transfer distance. That's the distance between the centroid of the little area and the neutral axis squared. So,
could you repeat that, please?
Yes, sir. I was going to show you on the figure. It's a little easier to show. But the transfer moment of inertia is the area under consideration. You may have 5 or 6 little areas, so you take each little piece's own personal area, and you look at him and you see, is your centroid on top of the centroid I just found? And he says, no, I'm 6 inches up in the air. Well, then you multiply his area times how far his centroid is off of the neutral axis squared. Now let's go back to the one we just did. Looks like a kind of a T-shape. I'm going to find the location of the neutral axis. In other words, I'm going to find the location of the centroid. That number is y bar. Y bar is equal to 1/2 Yeah, it's 2 and 2 and 2, isn't it? So that should say 6 across the top. 1/2 times 6 times how far is he off of the x-axis? 1 and 12 and 1/4. So I'll go up 1 foot to get to here. I go up 12 feet to get to here, and then I go up 1/2 of 1/2, because the centroid of a rectangle is halfway up. So that's 13.25 feet. Plus, now I work with the second area. The second area is of magnitude 12 feet tall, 2 feet thick, and his centroid is 1 plus 1/2 of 12. 1 plus 6. Plus, I do the bottom area is 1 foot thick. It looks like it's 1, 2, 3. It's 4 feet wide. And it is 1/2 of a foot from my reference axis. You always ought to draw your reference axis at the base. That keeps you having to worry if whether or not these y bar or these y distances are above or below. You don't have to worry about that. Everything's above the reference axis. Then that number is divided by, and you simply recopy 1/2 times 6 is the area, plus 12 times 2 is the area, plus 1 times 4 is the area, and you crank out that number to find out where the centroid is. You also ought to be able to look at it and get pretty close. In other words, if the answer that you get now comes out 16 feet, well, there's something wrong. There's no way it's 16 feet. If the answer comes out 2 feet, there's no way, because I could not cut that out of a piece of cardboard and bring it to my kitchen and balance it on a knife 2 feet above the bottom. It would keep flopping over on its top. So I'll say, before Kelly gives me the answer, it looks like it's right about here. Oh, maybe 10 feet. Maybe 9 feet.
Turns out it's 8.08.
8.08 feet? I love it.
I'm double checking.
Okay. In other words, you're saying don't write it down just yet. 0.5 times 6 times 13.25 plus 12 times 2 times 7 plus 1 times 4 times 0.5 is equal to, divided by parentheses 3 plus 24 plus 4 parentheses close equal.
I get 6.77.
That's what I get. Same number, 6.77 feet. Okay. Now then, to get the moment of inertia. The moment of inertia should be calculated about this neutral axis. The moment of inertia is equal to the sum of all of the I0 terms, and everybody always has an I0 term. That's I0 stands for I, his own personal moment of inertia. If it's a rectangle, be h cubed over 12. If there was a triangle, we would get the moment of inertia out of the book for a triangle about its own centroid. So we have, for area up on the top, let's call that one area 1, we have his base times his height cubed divided by 12, just because he came. Just because he's there, he gets a 6 times half cubed over 12. If that were a circle, it would be pi d fourth over 64, I think. I know it's in the book. If it were a missing circle, I would take that term as a negative term because it was a missing circle. We don't have any missing pieces here. To that, I'll add the moment of inertia of the web, the middle piece. Its base is 2, its height is 12, cubed divided by 12. I add the moment of inertia of the little bottom part. Its base is 4, its height is 1, cubed over 12. Now we ask these people, are you right on top of the neutral axis? If he says, no, my centroid does not lie right on the neutral axis, then he also adds a transfer moment of inertia. Transfer moment of inertia for area 1. Area 1 is up here, and that distance you can measure with a ruler or you can calculate. It is 13 1/4 minus 6.77. That's Y1. Or I guess we call that D1 because we call the other guys Y's. How far is that?
It turns out 6.4.
In your neutral axis, just below where you're showing it, below the centroid of the middle member?
It sure could be. See, I don't know that, to tell you the truth, because I kind of committed to drawing it before we started. So it wouldn't bother me if it was a little below. Once I calculate the real distance, I'm going to square it anyway, so that would be okay.
It turns out 6.48.
This number right here, 6.48. Okay, now let's see if it really is a little below. A little below this number here. This number right here is 7 feet high. You're right. The neutral axis was incorrectly drawn when we first guessed it. But I'm not going to, like I say, I won't worry about that. I'll be careful to take it into account. Alright, so here's area 1 is a 6 by a half. Here is D1 is 6.48, and that number gets squared. Next, we'll take into account the little middle piece. The little middle piece is 2 feet across and 12 feet deep. And he is off of the neutral axis by the following amount. His centroid is personally 7 feet high, and as you noticed, the Y-bar is only 6.77 high, so the difference between those two is 0.23 feet, and that number is squared. And we get a final term down at the bottom. His centroid obviously is not on the neutral axis. It is 6.77 to the neutral axis minus he is 1 foot off of the reference.
0.5.
Ooh, thank you. And that's the distance. We still got to have the area. We've got to remember to square that distance. And the area is 1 by 4. And you crunch all those numbers out, and that's the moment of inertia of that shape. Alright. Now, if that wasn't used in so many problems, you know, I just don't know if it'd be worth all the time it takes to do that, but that stuff just appeared over and over and over again. All right, I'm going to skip page 22 and go to 23. 22 is really just like the rest of them. It's just another example of I0, which you look up in a book or in a table, and the AD squared terms, which you calculate. Because what I want to do is show you how to get the moment of inertia or how to get the centroid of a concrete or a mixed beam. Anytime you have a section that's made out of more than one material, for instance, here is the concrete modulus of elasticity, and it is not the same as the steel's modulus of elasticity. Then you have what is known as N is a modular ratio. And that modular ratio is simply E big divided by E small. They always use the big one over the small one. In our case, it is equal to 29 divided by 3.2, because it doesn't matter where the decimal goes. 29,000 over 3,200, that's okay. 2.9 over 0.32, doesn't make any difference. It's just a ratio.
9.0625.
And that's 9.06, which is telling you that the steel is 9.06 stiffer than the concrete, and in effect will resist bending and will have moment of inertia contributions 9.06 magnitude of what concrete will give you. So the easy way to do them is just to pretend this is not a steel concrete beam, it's just a concrete beam, where the area of concrete is just bigger than it looks, namely 9.06 times bigger than it looks. The steel looks like it's 20 square inches of steel. If we replace that with an equivalent area of concrete, we simply multiply 20 times 9.06. I hope we get 181.25.
Correct.
Good. And that's just like concrete. And no difference at all. Just go ahead and say it's now a concrete beam. And all the calculations proceed from there. Now on the next page there's a quick equation which you can use to find the distance C, which is the depth of concrete before it cracks. Remember that since concrete cracks below that area, the concrete in effect, or below that axis, the concrete's really not even there. These calculations for C and for moment of inertia are used when you design concrete beams for deflection calculations. And the equation on page 23B is simply N times area steel over B times square root. You know, you could derive that thing, but who cares? You believe that, I believe that. N would be our 9.06. Area of steel, in that case, would have been 20 square inches of steel. Hey, Keon. Figure.
You know where he's at?
14 inches. Is that page in there, Chris?
Yep.
No, I don't think so.
You don't have page 23B?
No.
Ooh.
Yeah.
All right, there we go. C is equal to the modular ratio times the area of the steel in the beam divided by the base of the beam times the square root of 1 plus 2 times the base of the figure times the depth of the beam divided by the modular ratio times the area of the steel. After you take that square root, subtract 1 from it, you put parentheses around the whole thing. And there are, in your book, I believe it gives you how to solve for that. It's just not worth it. It's just too easy to solve for C right out of this equation. So we plug in our 9.06. Our base was 14 inches. Our area of steel was 20. Our base is 14. How deep is it? So I don't have to shift this page again. 28, thank you. Our area of steel is 20. Our modular ratio 9.06. We crank that out and you'll find that's the location of the neutral axis for a concrete beam.
16.9.
16.9
What
inches.
were the numbers you put in?
Very straightforward.
I can't see them.
And if one of those doesn't come out, tell me. All right.
It's great numbers.
I actually think we're going to get finished with this. That's pretty good. I was not feeling real good about that. All right, here we go with a bolted connection. That's page 24A. I hope they didn't. Did they get that one in there?
Yeah, we got that one.
Good, because that'll be hard to draw.
That's 24, I don't know, 24.
Alright, here's how we'll find the location of that group of bolts. We'll draw a reference axis on the left edge. And due to symmetry, I'm going to go ahead and draw a reference axis across the top edge. As long as all the bolts are on one side, I don't care. I just don't want half the bolts to the right and half the bolts to the left, because then some of them will be plus, some will be minus. Phooey on that. Y bar is A1, Y1 plus A2, Y2 plus dot, dot, dot. The old famous dot, dot, dot. Divided by A1 plus A2 plus dot, dot, dot. Where area is just a bolt. Is equal to. I got 3 bolts. Whoops, thank you. Glad somebody's watching out for me there. I got 3 bolts having no distance away from the reference axis. Plus I got 2 bolts 3 inches away from the reference axis. Plus I got 1 bolt 6 inches away from the reference axis.
9.
Thank you, sir. I knew there's a reason I paid you to come to this. Check's in the mail. Divided by, I got 6 bolts. Does that come out, Kelly? 6 plus 9 over 6. About 2.5. Correct. 2.5 inches. That's where the centroid of that bolt loop is. Right through there. And because of symmetry, the other one is the same.
It's not symmetric.
Not symmetric? Ooh. You're right. Thank you. It sure isn't. So I found Y bar. Good. X bar is equal to. I got 3 bolts right on the neutral axis. Plus, I've got 2 bolts 2 inches off the neutral axis. Plus, I got 1 bolt 6 inches off the neutral axis. 9 inches. Now, going this way is 6. 6. Okay. Yeah, I was a little confused. I think you'll find this problem is in your example quizzes, and I changed them a little bit because I really didn't like it being symmetric. Then I forgot I changed them. Okay, divided by 3 bolts plus 2 bolts plus a bolt. And that tells me X bar. 1.67 inches. Now then, bolts have a moment of inertia, exactly like, incidentally, all these calculations are on page 24. We have a moment of inertia due to the bolts. The bolts are too tiny to have a moment of inertia about their own centroid, so we throw out their I0 terms. And all that's left, because they're so tiny, is their AD squared contributions. The quickest way to find this moment of inertia is to sum up all of the X squared numbers. By that I mean if a bolt has an X distance off of the neutral axis, you add him in and you square him. So that says, I'm talking about the X distance now. There are 3 bolts, and they are negative 1.67 inches off of the X, off of the Y neutral axis. That's their X distance. And you square it. Then you add in the fact there are 2 bolts, and they live 0.33 inches off of that Y axis in the XX direction, squared. And then there's 1 bolt, and he is 4 1/3 inches off of the Y neutral axis, squared. And that's one number. Then you do the same thing for the Y terms. And those calculations are shown on
I think it's their external force.
On page 24.
Yes. Force external.
And you simply add up all the x here. You add up all the y squared. And the whole mess is the sum of the x squared numbers plus the sum of the y squared numbers. It looks like we already totaled these out. One of them is 27.33. One of them is 61.5. Now then, to find how much force there is on any bolt, you take the moment that's applied and you divide it by the moment of inertia. That'll tell you how much force is acting on any bolt, depending on how far it is from the centroid of the groove. So, here is what they call K, kind of like a load rate. Take the load, you multiply it times how far is it off of the centroid, and you divide it by I. In our case, we have a 10-kip load. This guy is this far off of the neutral axis. 2 plus 4 plus a third. 6.33 inches. And you divide it by I. What does that 27.33 plus 61.5 come out?
88.83.
88.8. Thank you. What that guy is telling you is, I don't care where your bolts are, they will have this many kips every inch away from the neutral, every inch away from the centroid that they live. So for instance, you see this bolt way out here? You find that distance right there by trig, multiply that distance times 0.713 kips per inch, and that'll be the total force acting on that bolt. So you can design that bolt. An example is down on the bottom of page 24. Now, excuse me, that force I just told you, that slanted force, that force is due only to the moment. See, because that's only due to the 10 kip times the 6.3. There's another force acting straight down, and that's simply equal to, let's see, F sub y is equal to 10 kips divided by 6 bolts. That's the direct shear component. I take it there's really no way to get the feedback from my voice out and leave their voice in.
Somebody's got their monitor, their mic on. They're on mute right here. They couldn't hear us.
Right.
That way, if we were talking, we wouldn't give you feedback like that.
Okay.
But somebody else has got they got mics all over on their tables.
I got you.
Somebody got the
Okay, I was just curious. It's always strange to hear you talking back to yourself. I keep thinking somebody's got a question. Keep saying, well, somebody answer that dumb guy's question back there. All right. Let me mention that Fy force is what they call direct shear. It is as if the 10 kip load were acting right through the centroid of the shape, 10 kips, and then we add on the moment part. You can split it up into components, makes it easier. F sub y due to the moment is the 0.713 that we just found, kips per inch out, and you simply multiply it times how far out is the bolt that you're studying. This bolt looks like it's about the furthest one out, and therefore it's probably got the highest forces on it, and therefore we study it. It is 4.13 inches in the x direction. Since it is in the x direction, it causes a y resistance force. And that gives you another y component of the force. It also has an x component, F sub x. And the F sub x component is found, shown on page 24. You simply multiply the 0.713 times how high up it is above the centroid. It's 2.5 inches above the centroid. Knowing all your f sub x's and all your f sub y's, you simply add them up as vectors, and you have to go find me a bolt that'll hold 4.94 kips on the bolt. You'll notice the 1.67 and the 2.94 on bottom of page 24. They're just added because they're both y components, so they just get added together, and then the x component has to be added as a vector. Now, there's been a couple of problems we've seen, and people told us about where the bolt patterns look like you see here. Most of the time when they look like that, they just ask you how much force was on the bolt. They didn't go ahead and design it. Usually if you have a nice bolt pattern where the bolts are, say, like this, you know, something nice and neat, those will be available to you in the AISC tables. You can go get everything you need to design those right out of the tables, and Pete Keating will be discussing that kind of stuff. Alright, now, just between you and me, I don't care how long we stay here. We can answer questions all night long. It is 9 o'clock. It's supposed to let everybody, you know, sneak out if they need to go home, and their wives say, look, it's your turn to take care of the baby. I don't blame you. Kelly, I brought Kelly for moral support, for working the camera. Work that camera for me, Kelly. Look at that. What an expert. Zooming in, zooming out, working the numbers for me, watching out my mistakes for me, which he's done admirably. The main reason I did is because Kelly just passed the exam. And probably can really answer questions on what it was like, what you should have brought, what he didn't bring he should have brought. If I was out there getting ready to take it, I think I would be quite interested in that. I'm not sure if anybody is or not. You know, you may say, look, I'm taking everything I got, and I'm as ready as I'm ever going to be, and that's why I'm taking the class. But has anybody got any questions about somebody who just took it, just passed it, just saw it, went through the grief? Zoom, 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 zoom over, pan right, pan left.
Does anybody have any questions that we can address?
All right, well, see, I thought that would be of interest, but can't win them all.
Well, just to let you know, just a couple of things that I experienced in the exam. It is a very long exam. It's an exam in which you need to pace yourself. You have 4 choices in the morning, 4 choices in the afternoon. You pick the 4 choices out of the 12. You need to try to time each one of the questions out. And probably the best thing that I found out was to start off with the easiest one. And if you did that, the first one, in 30 minutes, then you know that you can base your next problem out and say that you're moving along and it takes you 30 more minutes on the next problem. Then that leaves you still 3 hours to solve the next 2 problems. But to be honest with you, most of the time I found that each one of the problems will generally take you an hour for the morning session. Try to base each one of the questions that you try to work, and try to work it within an hour. If you do it less than an hour, great, you're that much ahead. If it takes you longer, then maybe you need to start thinking about trying to move on, because realize that the question is graded based upon a scale of 10, and you need to get so much of that. If you don't get the exact right answer all the way down to the fine answer, then you're going to get graded for what you know and what you do on the problem. So remember that part of it.
Now that's in the morning, right?
That's the morning session.
Okay.
The afternoon session, you will have to mark the dots. You have a choice of 5, I believe, or 6, well, 5 dots, A, B, C, D, E. And that is a little bit more difficult. But still try to take a look at the problem and try to work it and really try to average your time out, and you'll come out ahead in the long run. Any other questions that I might be able to answer for you?
All right, Chris, thanks for being my guinea pig over there. Let me give you a telephone number. 409-845-4395. Just ask for Lee. That's me. Chris, you got email down there?
No. I don't, at least.
Anybody in the room got an email address?
We can probably do it, but we have to put it on the communication system or the DOIM, because it's got to add yours to our list.
All right, you want to do that?
It's up to you.
All right, if you would do that, it would sure make it easy for us to communicate. If you say, I got some needs, you need to do this, you need to stop using white paper, I mean, anything like that, you can just email me. It really would be quick and fast, and I check the email constantly. I'm at LLL2761 at zeus.tamu.edu. Chris, does this white paper come through glary, and is the blue paper better? Or does it really matter?
Doesn't really matter.
Great, okay, I appreciate that. All right. Also, I don't have any idea if you have an interest in this or not. Kelly was determined to pass this quiz and bought $500 worth of videotapes covering this material. It proved to be, when I looked at it, very similar to what we thought would be in your best interest. But I'm not sure everybody came tonight, and I'm not sure that you may not want to take a look at them and review them. If you want to, I'd be happy to send them down to you. All I need to know is if you want them. There are 12 tapes. I didn't pay $500. I paid half that much. I got a deal. They cover, everything that we're going to cover, maybe even a little more. Maybe their interests they thought would be a little more surveying, a little less economics or whatever like that. But to me, I thought they were really pretty good tapes. If you got time for that, if you want to view them, if you'll just contact me and say, send them down and I'll watch after them. Anybody who wants to volunteer to that, just tell me. I'll stick them in a box and I'll ship them to you. I also truly do have in the library, every bookmaker in the country sends me tons of stuff, hoping we'll use it for our 20,000 engineering students. I got tons of old strength of materials books, not old ones, new ones, structural analysis texts, statics, dynamics. If you'll just write down what you'd sure like to have a copy of, till I run out of things, I'll stick my name all over them, ship them down to you. It'd be best if I can ship them in one box at one time, and be happy to loan them to you. When you're through after the quiz, ship them back to me, and anybody can get some good out of that, let me know. This email address you're going to add on yours. Then what would you do? You'd add me to your node set and write me an email address, or write me a message.
What we got is Profs is a IBM system that we can communicate on internet. However, we have to put the internet address on our mainframe.
All right, is that a problem?
No, it shouldn't be. I'll check with the people tomorrow.
All right, is this the kind of address you're looking for?
We can make use of that, yes.
That's the kind, okay. I mean, I got internet addresses besides that, like I got a Gopher machine in my office, and I got a Mosaic, and if you find one of those are more convenient, you know, you just have to let me know, and I'll give you those numbers.
That's your LLL2761 is you, and the rest of it's your user computer and TAMU. I understand. It should work. I send stuff to my kids from my American Online, too.
That ought to do it. In fact, if you've got an AOL account, you know, I could write to your, but that'll cost you to hitch up, doesn't it? I missed.
Not a problem. We can do it both ways.
All right. Well, so if you have any trouble adding me to your end of things, then I can certainly hit you at AOL. Best I remember, you got about 10 or 12 numbers, and then at AOL.com.
Yeah, I mean, everybody in AOL, everybody's got like their own user ID, and it's AOL.com. You're right.
All right, that'll be.
But we'll try to put you on our PROV system here, because most people have access and work on that.
All right, sounds great. And I just think that cheap, inexpensive communication like that would be worthwhile. I mean, I know we can call each other and say, "How are we doing? Do we need to do this?" That kind of stuff. But if it costs 20 cents, nobody will do it. This stuff's free. Okay, any questions on anything we've done? Okay, gentlemen.
Do we have another handout for next week?
Tell me that again.
Is there another handout for next week, or are we going to continue with what we have?
No, sir. There's a little bit probably left over in your packet, but there'll be new notes coming to you before we meet on Wednesday. Or Thursday, or whenever. With Wednesday? Okay, be Wednesday. No, it'll get to you before Wednesday. Appreciate it, gentlemen. See you.
Thank you.
Thank you.
Thank you. Oh, look what, is that what we've been sending them? Give me a picture. Oh, wow.
What is your cobweb?
Thanks, Chris.